Hello, welcome back to Mastering Statistics. If you've been following the lessons thus far in analysis of variance, you should be pretty happy because we've solved one problem, and it took a lot of sections to do it. I had to get into a lot of details and talking and equations to even get to this point, and we now know how to solve one of them, but the problem with splitting everything up into 10 sections is that you kind of lose sight of the big picture sometimes. So this is going to be just a summary section, hopefully not too long, basically going to summarize in one place everything that we have done to give you the big picture if you may have lost sight of it a little bit. Then we're going to go on and use the computer to solve problems, and you'll kind of like solidify your understanding of everything. So basically, an analysis of variance, you have population. So in this case, let's say population 1, population 2, population 3. And you should have in your mind the example that we did, which was the average age of marriage of women. So here's population 1, could be thousands of people. Here's population 2, which could be thousands of people. Here's population 3, which could be thousands of people. Now, we can't actually sample everybody, so we go in here and we take a subset that we call samples. We sample from here, we may take 10 or 15 people or whatever, and then we sample from here, and then we sample from here. We do not have to take the same number of samples from every population. We could take 6, 25, and 37. The Anova test is going to work fine. It's going to take all of that into consideration. So anyway, we have some sample data from every population. Now our null hypothesis is always going to be the same thing. The null hypothesis is always going to be that the population mean from number 1 is the same from population mean number 2 is the same from population mean number 3. And the alternate hypothesis is just going to be that one of these three population means, or more than one, is different from the others. So either they're the same or at least one of them is different. That's always going to be the same thing for all of these problems. Now, we're going to crank through the steps real quickly. The first thing you always do is you find what we call the grand mean. And we denoted that X double bar. Basically, it is the average value or the mean value of all of the samples that we collect from all populations. And it serves to be the baseline that we're comparing all of these individual sample means to. So basically, you collect all the data, add everything up, divide by the number of samples, you get something that we call the grand mean. The next thing you do is you find the sample means. And we denote those as X bar 1, X bar 2, X bar 3. And that is just the average of these samples. And then separately the average of these samples, and separately the average of these samples. So we get the grand mean, which is all of the guys averaged together, and the individual sample means. The next thing we do after that is we find something called the sum of squares among treatments. We call that SST, the sum of squares among treatments. And the way that we calculate that is n sub 1, I'm going to write it out like this instead of with a summation symbol, x bar minus the grand mean squared plus the number of samples that we took from population 2, x bar 2 minus x double bar squared plus we're going to have n sub 3, and inside here, x bar number 3 minus x double bar squared plus dot dot dot, depending on how many populations you have. Look at what's happening in here. We're just taking the sample means and we're comparing it by means of subtraction to the baseline, the grand mean. Sometimes this number will be positive, sometimes it'll be negative, depending on if the mean is above or below the grand mean. But anyway, we take it, we square it. We take the next one, we square it. We take the next difference of this sample mean and square it. Okay, that's a sum of squares among treatments because these guys are also called treatments in Anova. Now, once we take these squares, we multiply them by the number of samples that we took each time because this is a weighted average. So from population 3, if we only took 2 samples, for instance, then this difference here is not going to count for as much because we're only going to be multiplying by 2. If population 2 came from 94 samples, it'll count for more. So we're trying to figure out how much variance or how much variation there is of these sample means there are to the baseline, which is the grand mean, but in a weighted average where more samples count more because they have more validity, right? That's called the sum of squares among treatments. Then we take that number that we call the sum of squares among treatments, and we find the mean square among treatments, which is just simply taking that number that we just calculated and dividing by the number of populations we have, but with a small correction factor, k minus